Okay, in this video, what we're going to do is we're going to start with the definition of derivative. I'll regurgitate the definition in general of what's happening with the definition of derivative. Then I'll do the last algebra case of conjugating, and then we'll combine the two with a common denominator and a conjugation. And then there's a few other caveats, but essentially that will give you a way of computing the definition of derivative using these limits. And then we'll start the little rules of differentiation so that you don't have to use the limit definition. This is going to get you around eventually having to use the definition, but they first want to know whether you know how to compute the definition. So example 3, example 1 was a polynomial. Look at the previous video. Example 2 was a rational function or a fraction. Now example 3 is going to be, we're going to have a radical. Let's put it in the numerator. So let's let f of x just equal x plus 1 square root this time. So in the last one we had 1 over x plus 1. Let's do x plus 1 square root, or x plus 1 to the 1/2. How are we going to do this by definition? Let's do that one. Again, so the solution is regurgitating the definition. F prime of a, by definition, is equal to the limit as h approaches 0 of f of a plus h minus f of a over h. If you want to start putting it all in there, I like to prep it, but for the radical it won't be too crazy. This will be, what we have is the square root of a plus h plus 1 minus the square root of a plus 1. That's f of a plus h. That's f of a over h. Or you can do it separately. F of a plus h is the square root of a plus h plus 1. To see what it is first, f of a is the square root of a plus 1. I now see I can't simplify those expressions any. I just put them into the pot. Now what do I do? Because I need, the real mantra is get an h out of there. So what should I do? It should hit a Pavlovian nerve. I should be doing conjugate. So I do the square root of the first one, the square root of the second one, plus, but then I can't just do that. That's crazy. So I multiply by 1 in the form of the conjugate. Now I've multiplied by 1. It doesn't change anything, but on the top will give me an h. What do I get here? This is the limit as h approaches 0. Now I get whatever was underneath the first square root minus whatever was underneath the second square root over h times that hot mess. Now the square root of a plus h plus 1 plus the square root of a plus 1. Now we can cancel. Anything without an h should cancel off, and it does. And what are we left with? We're left with just h, and then the h's are going to cancel. But be careful, write this out again. This is the limit as h approaches 0 of just h over h times the square root of a plus h plus 1 plus the square root of a plus 1. Now the h cancels, and we get equals the limit as h approaches 0 of 1 over the square root of a plus h plus 1 plus the square root of a plus 1. I ask myself, where am I going again at every step? H, it's not a problem anymore because I just canceled it. And so this one goes to 0, and we get 1 over root a plus 1 plus root a plus 1, which is 1 over 2 root a plus 1. This is the definition of derivative. The next example that I'm going to do is we're going to do a combination of a rational and the radical. So we'll do 1 over the square root of this guy, and then we'll have to do both dirty tricks. It turns into a nightmare, but everything will happen, and then we get a number. Let's do that, and then we'll do some of the rules. Okay, example 4. Combining 2 and 3. Examples above. So let f of x equal 1 over the square root of x plus 1. So now I have the fraction and I have the square root, the radical. So I'm going to have to do both dirty tricks to get the h out of the top of this definition. Solution. First of all, f of a plus h now is going to be 1 over the square root of a plus h plus 1. F of a is 1 over the square root of a plus 1. And so f prime of a is equal to the limit as h approaches 0. I leave the h on the outside because it's a fraction again. If you're doing it right, that h will cancel. But where am I going h? Is it a problem? Yes, always. That's why. And then now what do I have? 1 over the square root of a plus h plus 1. I am leaving some space over the square root of a plus 1. I leave some space bracket. Why? Because this one, I need a common denominator. The first thing we have to do is rectify that, and then we're going to rectify the square root, is what I see. Conjugate. Common denominator. It had to be both tricks. So first is the common denominator. And so I'm going to multiply by root a plus 1 over root a plus 1. This one is missing, root a plus h plus 1 over root a plus h plus 1. Now that I've done that, I don't want to write that out and I'm lazy. So now I see I have to get rid of a radical on the top. So I'm going to conjugate and multiply by the square root of this one plus the square root of a plus h plus 1 over the square root of a plus 1 plus the square root of a plus h plus 1. The second dirty trick. Now that I do that, yes, we'll get a hot mess, but what are we going to get? On the top, we get equals the limit as h approaches 0 of, now we have the 1 over h still, and then I have whatever's underneath the first one, a plus 1 minus a plus h plus 1 over that hot mass, a plus h plus 1 times a plus 1 times the square root of a plus h plus 1 plus root a plus 1. All of that, close bracket. Now, that got a little bit crazy, but it will go back to cancel, 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 cancel. We have a negative on there. Careful, it goes on to all three. Then we can rewrite this as equals the limit as h approaches 0 of negative h over h times the square root of a plus h plus 1 times the square root of a plus 1 times the square root of a plus h plus 1 plus the square root of a plus 1. I really didn't want to do that, but the h's cancel now, which equals, I'm going to just write the answer, negative 1 over, what do we get now? H is going to 0, h is going to 0, so we get root a plus 1 times root a plus 1 times root a plus 1 plus root a plus 1 when the h's go to 0, which gives us what? That's 2 of them. So we're going to get 1 over 2 times a plus 1 to the 3 over 2. If you check, that's the number we get. That is how we do in worst case scenario almost. There's a couple other caveats that they can give you some horrible functions and make you do the definition, but otherwise the main tricks are foiling or expanding everything, the h when you get a polynomial, or using a common denominator, or using a conjugate, or using both like we just did, and you get your finite number, the derivative f prime of a. All right, let's do some of the rules which will speed this up if you know the derivative. And then in the next video in 5.3, I'll give you a rant on how to use the rules and not get around the derivative. We only go back to the derivative in a new category of functions like trig. We have to use the building blocks. Right now, the building blocks of all these rational functions or algebraic functions are polynomials and then rational functions. So starting from polynomials, if you can build it with a finite number of operations of plus, minus, multiplication, division, and nth roots, we call that algebraic. Using the rules now, we can get at their derivative if we know the derivative of polynomials is the idea of this. Let's go through a couple, the major ones. The first couple rules are just the obvious things that they want you to have, which are, let's just do rule 1, R1, we'll call it. Also, let's do notation first of all. Notation, notation, notation. First of all, we have Newton, Sir Isaac Newton, or Leibniz, who invent calculus. In this, we're going to use f prime of x is the symbol we're going to use. In this one, we're going to use df dx or dy df of x or dy dx, because y is f of x. is the notation. So this is Leibniz notation versus Newton's notation. It means the same thing. F prime of x equals dy dx. It's the derivative or instantaneous rate of change. Also, the definition of the derivative at every point is the same as at point-wise. We would say the limit as h approaches 0 of f of x plus h. You just replace the x with the a minus f of x over h. This is the derivative as a function, and then you can compute. So now if I have the derivative as a function of some other functions, e.g. if I let f of x equal x squared, we saw from the previous one that f prime of a will be 2x, or in general, if I replace the a with the x, the derivative at every point is 2x. If I now want to know at any value f prime of a, this will be 2a, or if I want to know f prime of 2, this will be 2 times 2, which is 4. So I can compute the derivative at any point now if I view it as a function. So this is the derivative of x squared is the straight line 2x. They are related to each other as this is the derivative of that function. Now let's do some of the rules. What the rules are going to say is if you know the derivative of a couple functions, I can use formulas to do derivatives of horrible algebra. That's what we're going to get at. Now let's do rules. Rule 1. These ones seem superfluous, but they like to put these a lot just to be careful. First of all, I want to know that the derivative of all polynomials is what I want. So if we have that the derivative f prime of x or f prime of a is equal to, I should be editing this now because I have rule 1. If I have that f of x is equal to x, then f prime of x is equal to 1. The derivative of x is just 1. That should be the first rule, or the first thing you want to know. Also, rule 2 is going to be, we did it, but let's do it in general. The derivative of, which they're going to call the power rule. This was just a special case of n, where n is any positive integer. This is going to say that the derivative of this function is going to be the derivative with respect to x of x to the n in Leibniz notation is going to be n x to the n minus 1. We prove this using the binomial theorem and the definition. It's horrible, but we're just going to list it as some of our first basic rules. So the derivative of this guy is that guy, and then rule 3 is I can deal with everybody. What's the derivative of f is just a constant. I put this in a weird order, but it doesn't matter. So if this is just a c inside r, then what's the instantaneous rate of change of a function which never changes? It should be 0. Then f prime of x is equal to the derivative with respect to x of a number is always 0. So the derivative of constant terms in a polynomial are 0. The derivative of just an x term is 0. The other thing that we're going to use now is, let's use derivative rules. Let's switch. These were the rational functions, or the ones that I needed for the polynomial specifically. Now the derivative rule 1 is going to be, if I have the derivative with respect to x of a constant times a function, it doesn't care about the constant. I can write this as c times the derivative with respect to x of f of x. So you can pull out the constant out of a derivative. It doesn't care. The second one I want for this derivative, and then I can show you in this video, and then I'll add a few more derivative rules in the next video, or I can list them all here and then I'll relist them. But the second one I want is sum. If I know the derivative of the first function, I know the derivative of the other one. When I add those guys algebraically, what's the derivative? So the derivative with respect to x of the sum of two functions, or minus, so I'm going to be lazy, of g of x is equal to the derivative of the first one, f of x, plus or minus the derivative of the second one. And why I want to stop there is with these ones and then this, I can get the derivative. Let's do an example where I did the derivative of all rational functions, or all polynomials. First, we'll do the derivative of every polynomial. Let's do that, and then we'll list a few more. Example, find the derivative of all polynomials. So p of x is now going to be a n x to the n plus dot 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 plus a1 x plus a0. Find the derivative of any arbitrary polynomial. I'm going to use the rules and the first power rules, etc., and some of the derivative ones. So what is this? This is the derivative with respect to x of a n x to the n plus dot dot plus a2 x squared plus a1 x plus a0. There's an arbitrary polynomial. Then what can I do? First of all, I know that I can use d2 because this will be equal to now, specifically, what? I can distribute this onto everybody. So this will be the derivative with respect to x of a n x to the n plus, technically by induction, but then it will be derivative with respect to x of a2 x2 plus the derivative with respect to x of a1 x plus the derivative with respect to x of a0. The next one I'm going to use without writing it down is, I'm already being lazy, but with the rule I can say that this is 0 by property R3. The derivative of a constant is 0. Now what am I going to do? I'm going to use D1 to factor out all of these constants outside of the inside of there. So I cheated and used R3 to say that the derivative of a constant is 0. He goes away. So I split the sums. I said he's 0 because he was a constant. For every other term, I can split the constant out. So this will be equal to, by D1, he's equal to an, the derivative with respect to x of x to the n, plus dot 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 plus a2, the derivative with respect to x of x squared, plus a1, the derivative with respect to x of x. This one is also 1 by our property 1. But all the other ones are going to be by property R2. The power rule is what it's really called. Now what can I do? The derivative is going to be an n x to the n minus 1 plus dot 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 plus a2 times 2x plus a1 times 1. And then that's the derivative. So what is the derivative of every polynomial? It goes to a derivative, or it goes to a polynomial of degree 1 less. So p prime of x is always equal to an n x to the n minus 1 plus dot 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 plus a2 times 2x plus a1. That's the new polynomial you get from the original polynomial from taking its derivative, and it's of 1 less degree. So it'll disappear eventually if you keep taking derivatives, because you'll just get a constant eventually, and that'll be 0. We'll use that later in other classes. I'll see you next time, and I'll list the rest of the derivative rules and start showing you the other algebra, including the chain rule.